In this review, we'll look at dispersion modeling. The dry adiabatic lapse rate is the rate at which dry air cools adiabatically with increasing altitude. Note here that the lapse rate nomenclature is inversely related to the change itself. If the lapse rate is positive, the temperature is decreasing with height. On the other hand, if the lapse rate is negative, the temperature is increasing with height. The actual lapse rate is defined in exactly the same manner. And note that if the environmental lapse rate is less than the dry adiabatic lapse rate, the stability condition is unstable. If they are equal, it's neutral. And if the environmental lapse rate is less than the dry adiabatic lapse rate, then it's a stable atmosphere. So let's look at this problem here. When the environmental lapse rate is equal to the dry adiabatic lapse rate, the stability of the atmosphere is said to be, choices are neutral, unstable, stable, or super adiabatic. The answer is neutral. And just to help you recall, when we talk about super adiabatic, we're talking about the lapse rate. So the lapse rate would be considered super adiabatic. And this is the condition where we have an unstable atmospheric condition, and the temperature, so our environmental lapse rate, is falling at a rate greater than the dry adiabatic lapse rate. So let's look at this problem. We're given the following temperature data shown in the table here. We can first, let's calculate dt dz. So that's T2 minus T1 divided by Z2 over Z1. And that's 17.2 minus 20.5 divided by 347 minus 10. Let's add the units, degree C, meter. And that is equal to negative 0.0098 degrees C per meter, or negative 9.8 degrees C per 1,000 meters, or per kilometer. So the environmental lapse rate, remember, is equal to negative delta T over delta Z, and that is equal to negative times negative 9.0, and therefore that is positive. So it's 9.8 degrees C per kilometer. And remembering that the dry adiabatic lapse rate is also 9.8 degrees C per 1,000 meters. Therefore, the dry adiabatic lapse rate is equal to the environmental lapse rate, so the condition is neutral. Now, dispersion models are used to quantify the transport of pollutants as a function of both the source emissions and the meteorological conditions. There are a number of assumptions inherent in the dispersion model, and I've listed a number of them here. So, for example, the rate of emissions from the source is constant. We'll use the notation Q for the rate of emissions. The atmospheric stability is uniform throughout the layer into which the gas stream is emitted, so we'll assume that it is constant over the area that we're considering. The wind speed is also constant with time and elevation, so it's not changing over the period of time that we're considering. The pollutant we're looking at is conservative, so we're not looking at degradation of a pollutant, so we're assuming that there is no decay. The terrain is relatively flat and open. Also, the contaminated gas stream is emitted into the atmosphere at a distance equal to the physical height of the stack plus the plume rise. And we refer to that as the effective stack height. The degree of dilution of the plume is inversely proportional to the wind speed. And the pollutant material is reflected back into the atmosphere when it reaches the ground level. And that's extremely important in the mathematical equations. We won't derive those mathematical equations, but it's important to know that that assumption exists. Now, from this model, we can determine the concentration as a function of the horizontal distance downwind and also the distance away from the source. So if we're looking at this is our source, we're looking at this is the plume is moving in the x direction. We can also calculate it in the y direction, so that's the direction away from the center line. Now there's no explicit relationship between Q and distance downwind. Instead, what we use a model that predicts the concentration of the pollutant in the horizontal and vertical directions by a Gaussian or normal distribution. So this is the general equation for the concentration as a function of the emission rate Q, the distance downwind, elevation, wind speed, and dispersion coefficients. Z is the vertical distance from the ground level. And as we mentioned before, the effective stack height is equal to the height of the stack plus the plume rise. We can simplify this equation for a concentration at ground level, and if that is the case, then Z is equal to 0, and the term shown circled in red just becomes h squared. So let's first calculate the effective stack height for this problem here. So you're given the height of the stack, and that is equal to 105.0 meters. You're told that plume rise is 25.3 meters, and you're asked for the effective stack height, and that is just equal to the sum of these two numbers. So this is equal to 130.3 meters. Now, if we're looking for the concentration of the pollutant at ground level and along the center line, then Z is equal to 0 because we're at ground level, and if we're looking at the concentration at the center line, Y is equal to 0, and the equation simplifies even further to the equation that we have here. Now, in many cases, and for instance in ENA 489, we've calculated the wind speed as a function of elevation. The thing to note here is that the reference manual does not give you the equation or a table of p-values, so it's very likely that you will not have to calculate the wind speed as a function of elevation. They would need to give you this equation. They would need to give you the p-values as part of the problem statement, and my guess is that's very likely that you would see a problem like that. Now, it's extremely important to be familiar with this table, as it allows you to determine the stability classification as a function of meteorological condition. So make sure you note the comments in the note section. So for instance, regardless of wind speed, if you're told that the conditions are overcast, irrespective of day or night, for instance, that will be class D. You're also given in the FE reference handbook these two plots in order to determine the dispersion coefficients in the y and the z directions. And these are as a function of both distance downwind, note this is in meters, and stability class. It does not provide the equations and the parameters that we used in ENE 489 to actually calculate these dispersion coefficients. So let's look at this problem here. And it's been estimated that the emission of SO2 from a coal-fired power plant is 1.65 kilograms per second. The wind speed at the height of the stack is 4.5 meters per second. The effective stack height is 128 meters. And you're asked for the concentration 3 kilometers downwind. You're told it's an overcast summer afternoon, and you want the concentration at ground level along the center line. So again, we'll need to look at this table here. And as I noted before, regardless of wind speed, if you're told that the conditions are overcast, then the stability class is D. Shown here are the two graphs from the FE reference handbook that you will use to determine the dispersion coefficients. And I've drawn the lines on the graph for expediency. So here we can determine sigma y as equal to 210 meters and sigma z is equal to 70 meters. So we've showed how to find sigma y and sigma z, but note that sigma z is equal to h over the square root of 2 for neutral atmospheric conditions, and we have neutral atmospheric conditions. So in this case, sigma z is equal to h over square root of 2, which is 128 meters, over the square root of 2, which is 90.5 meters. Not the 70 that we previously calculated. Use the graph for conditions other than neutral. Sigma y is equal to 210 meters. So using this equation here, C max is equal to 1.65 kilograms per second divided by pi times 4.5 meters per second times 210 meters times 90.5 e to the minus 1/2 128 squared over 90.5 squared, and that is equal to 2.26 times 10 to the minus 6 kilograms per meter cubed, or 2.26 milligrams per meter cubed, or 2,260 micrograms per meter cubed. So this is, in fact, the answer. Now, this last set of calculations that we'll do are used to determine the maximum concentration downwind. And in order to do that, we'll use this figure right here, which is the figure given in the FE reference handbook. You're also given an equation that you can use to calculate the ratio of C times U divided by Q max and the parameters that you need for that equation. But for the most part, I would suggest just using the graph that has been provided. So let's look at this problem here. And we have a similar situation. Again, we have an effective stack, the emissions from the stack. In this case, you're told that the wind speed is 6.5 meters per second. The effective stack height is 150 meters. It's a cloudy summer day, so we'd go back to that table to determine stability class. And if you do that, you'll find that the stability class is D. And you're asked then for the distance downwind that the SO2 concentration reaches its maximum level. So we'll use this graph here. We have an effective stack height of 150 meters. We look at the line for the D stability class, and then we read across here to determine the maximum distance, and then we'll read down to determine this ratio here. So using that, the maximum distance is 5.8 kilometers. And note that in that graph, that the distance is provided in kilometers. And then in order to determine the maximum concentration, we will again, looking back at this graph here, we're reading this value right here. And that is, so this is 1, 2, that is 3 times 10 to the minus 6. So writing down all of our information from the graph, we have CU divided by Q max is equal to 3 times 10 to the minus 6, 1 over meter squared. And we'll use this equation right here. So C max is equal to Q, 1.65 kilograms per second. Divide that by the wind speed at the height of the stack, which is 6.5 meters per second. And we multiply that by the value that we obtained from the graph, and that is equal to 7.62 times 10 to the minus 7, kilograms per meter cubed, or 762 micrograms per cubic meter. So quite similar to the concentration that we determined. So that slight change in stack height really didn't have much of a change in our maximum concentration, and really didn't have much of a change either on the distance at which that maximum occurs. So hopefully this helps you to review material on dispersion coefficients, and good luck on the FE exam.